In 2010, engineers at Iran's Natanz nuclear facility watched their centrifuges fail one after another. The machines spun out of control, vibrated violently, degraded. The operators checked every reading. Every monitoring system showed normal. There was nothing wrong, as far as the systems reported. Something was lying to them. A piece of software, later named Stuxnet, had been inside the facility for over a year. It had specifically targeted their centrifuges, subtly destroyed them over months, and simultaneously shown false data to the operators watching. This was a new category of weapon. Iran's uranium enrichment program at Natanz was the primary concern of Western intelligence agencies in the mid-2000s. Enriched uranium is required for nuclear weapons. Natanz housed thousands of IR-1 centrifuges, machines that spin uranium hexafluoride gas at extraordinary speeds to concentrate uranium-235. Disrupting this program through conventional means, diplomacy, sanctions, military action, carried enormous political costs. The US and Israel jointly developed an alternative, a cyberweapon that could reach inside a facility with no internet connection and destroy its equipment from within. The Natanz facility was air-gapped, not connected to the internet. Getting code inside required a different entry method. The delivery vector was USB drives. Intelligence agencies arranged for infected drives to enter the supply chain of companies working with the facility, contractors, engineers, suppliers. The drives contained Stuxnet, which would silently install itself on any Windows computer it touched. Stuxnet then looked for Siemens Step 7 software, the specific industrial control system used to program the centrifuge controllers at Natanz. If it did not find that software, it did nothing. Stuxnet exploited 4 previously unknown zero-day vulnerabilities simultaneously, an unprecedented investment. It used a Windows print spooler 0-day, a Windows task scheduler 0-day, a Windows server service 0-day, and a Windows shell LNK 0-day. Most sophisticated malware uses 1 0-day at most. Using 4 indicated resources and sophistication available only to nation-states. The malware also used stolen digital signing certificates from legitimate Taiwanese companies, Realtek and J-Micron, so it appeared to be signed, trusted hardware driver software. Once inside a system running Siemens Step 7, Stuxnet intercepted the commands being sent to the centrifuge controllers. The centrifuges at Natanz operated at a precise 1064 Hz, a specific frequency required for effective enrichment. Stuxnet modified the rotation commands periodically, spinning centrifuges up to 1410 Hz, then down to 2 Hz, in cycles designed to cause maximum mechanical stress without triggering immediate alarm. Simultaneously, it fed recorded normal readings back to the monitoring systems. Operators watched data showing normal operation while the machines were being deliberately destroyed. The damage was substantial. Iran's uranium enrichment capability was set back by an estimated 2 years. Approximately 1,000 of the 6,000 centrifuges at Natanz were destroyed or degraded. Iranian engineers attributed the failures to manufacturing defects, substandard materials, operator error, everything except what was actually happening. Stuxnet was eventually discovered in 2010 when it spread beyond Natanz to computers at companies with no connection to the nuclear program, an unintended consequence that its creators reportedly knew was a risk. The code escaped. Stuxnet permanently changed the threat model for industrial control systems. Prior to Stuxnet, the security community generally assumed that air-gapped OT networks were safe from cyber attack. Stuxnet demonstrated that air gaps could be bridged via physical media, and that once inside an OT network, sufficiently sophisticated malware could cause catastrophic physical damage while evading detection indefinitely. Every operator of industrial control systems, utilities, water treatment, manufacturing, oil and gas, updated their threat models in 2010 and has been playing catch-up ever since. The proliferation risk was the second major consequence. Stuxnet's code, once it escaped Natanz and was discovered, was analyzed exhaustively by security researchers worldwide. Its techniques, the PLC attack methods, the rootkit capabilities, the spoofed monitoring data approach became blueprints. Nation-states that could not have developed these techniques independently now had detailed working examples to study. Iran itself subsequently developed significant offensive cyber capabilities. The attack that inspired their cyber program was their own victimization. For critical infrastructure operators, the Stuxnet legacy is a set of specific security requirements. USB media controls, restricting or monitoring removable media, prevent the primary delivery vector. Application whitelisting on OT systems ensures only approved programs can execute. Network monitoring between IT and OT zones detects anomalous communication. And independent monitoring systems, separate from the ones being attacked, can detect the discrepancy between reported readings and actual sensor values that Stuxnet exploited. Stuxnet was the first time a nation used code to physically destroy infrastructure. It worked. It set a precedent. Every major military power now has an offensive cyber program modeled in part on what Stuxnet demonstrated was possible. The era of purely physical warfare, of bombs and missiles as the only tools of physical destruction, ended in 2010 in a uranium enrichment facility in central Iran. If you want to understand what happened when Russia applied the same logic with less precision and more aggression, our video on Sandworm, Russian hackers who blew up a power grid, covers the direct evolution of this doctrine. Stuxnet proved code could break machines. Russia took the same doctrine and aimed it at a nation's lights. Sandworm, the Russian hackers who blew up a power grid with software, follows that evolution. It is on this channel.